Hello, and welcome to my Exam 1 wrapper video where I'll explain how to solve problem number 3 in the exam in great detail. Alright, so here's the problem statement. Two thin hollow spheres about the size of a ping pong ball with masses m1 equals to m2 equals to 2 times 10 to the negative third kilograms have been rubbed with wool. Sphere 1 has a charge q1 equals to negative 3 times 10 to the negative 9 coulombs and is at location 40 times 10 to the negative second I hat, negative 20 times 10 to the negative second j hat, and 0 k hat meters. Sphere 2 has a charge q2 equals to negative 6 times 10 to the negative 9th coulombs and is at location negative 30 times 10 to the negative second I hat, 50 times 10 to the negative second j hat, and 0 k hat meters. Part A asks to draw a diagram of the situation showing the positions of the charges. Part B asks for the relative position vector pointing from Q1 to Q2. Part 3 asks to calculate a unit vector pointing the direction of the electric force acting on Q2. Part 3 asks to determine the vector electric force on Q2 by Q1. Part 2 asks how would the magnitude of the net force change if the distance between the two spheres was increased by a factor of 5. Alright, so here is the solution to part A. Draw a diagram of the situation showing the positions of the charges. So it's really just taking the xy coordinate system, plotting sphere 1 down here at 40 times 10 to the negative second meters I hat, and negative 20 times 10 to the negative second meters j hat, and taking sphere 2 and plotting at 50 times 10 to the negative second meters j hat, and negative 30 times 10 to the negative second meters I hat. Alright, so this is the solution to part B. What is the relative position vector pointing from Q1 to Q2? Well, we were given the position at Q1 and the problem statement, and the position of Q2 as well. Since sphere 1 is pointing to sphere 2, the position vector change is just the position at sphere 2 subtracted from the position of sphere 1. I like to think of it as final minus initial. So that being said, we subtract the I hat components of the two positions and the j hat components of the two positions to obtain this final position vector of negative 0.7 I hat plus 0.7 j hat plus 0 k hat meters. Alright, so this is the solution to part C. Calculate a unit vector pointing in the direction of the electric force acting on Q2. So we calculate the regular vector from the previous part, which was negative 0.7 I hat plus 0.7 j hat meters. This is the formula to calculate the unit vector from a regular vector, which is the unit vector is equal to the vector divided by the magnitude of the vector. So we take the original vector over here and we divide it by the magnitude of the vector, which is the square root of the sum of its individual components squared, and we obtain this vector, which is negative 0.707 I hat plus 0.707 j hat plus 0 k hat. And notice that there are no units at the end over here because the unit vector is meters divided by the square root of meter squared, which is meter over meter, which then results to be dimensionless. Alright, so now we come to part D. Determine the vector electric force on Q2 by Q1. So this is the electric force equation. F electric is equal to 1 over 4 pi epsilon naught times Q1 times Q2 over the magnitude of distance squared times the unit vector distance. So now we just plug in all the numbers which were either given to us or were calculated in the previous parts. This is 1 over 4 pi epsilon naught, 9 times 10 to the 9th newtons meters squared per coulomb squared. This is Q1, which is given in the problem statement. This is Q2, which was also given in the problem statement. This square root was the magnitude of the r vector, and then we just square that. So the square root goes away, so it's just the sum of the individual components squared. And this is r hat, which we calculated earlier. So carry out all that multiplication, we end up with a force of negative 1.17 times 10 to the negative 7th I hat plus 1.17 times 10 to the negative 2nd j hat plus 0 k hat newtons. Alright, so now we come to the last part, part E, which asks if the distance between the two spheres was increased by a factor of 5, how would the magnitude of the electric force change? We don't actually need any numbers here, other than the fact that the distance was increased by a factor of 5. So we have our original electric force equation, which we used in part D, and now we have our new electric force equation, where the distance has been increased by a factor of 5. So to find out how the magnitude of the electric force we change, we divide the old force by the new force and find what the ratio would be. So we carry out this calculation. We see that 1 over 4 pi epsilon naught is the same in both cases, so those two cancel. Q1 and Q2 have not changed in charges, so those two cancel. So now we're left with 1 over r squared times 1 over 5 times r quantity squared. Since 5 is a scalar, we can pull that out of the 5r squared term to get 1 over r squared equals to 1 over 25 times the magnitude of r squared. After doing some algebra, we see that we get the magnitude of r squared divided by 25 times the magnitude of r squared, and the two magnitudes squared cancel out to get 1/25, which means that the magnitude of the net force would decrease by 1/25. This makes sense since the distance term is in the denominator, so as the distance goes up, the force should decrease, since as the denominator goes up, the result goes down. This concludes my video report of solving problem 3 on exam 1. Thanks for watching.